Hi everybody and welcome to my presentation. I'm Flaminio Borgonovo, former professor of electrical communication at Politecnico di Milano. I'm now retired from the position, but not from the research, as I'm here to present this paper, which is entitled Polynomial Law, a better alternative to binary exponential backoff, co-authored with Luca Barletta. This paper deals with Aloha, the random access protocol that made it possible the modern radio and media access. It is used directly or embedded in almost all access systems and environments such as cellular systems, satellite systems, local area networks, IoT, and RFID. We could ask why we are still studying the Aloha protocol, a subject that has been on the scene for 50 years, during which time a huge amount of literature has appeared. The fact is that this protocol, simple as it is in its mechanism, is very difficult to analyze and still presents not completely understood behaviors. In this paper, we investigate the Backoff mechanism, that is, the mechanism that Aloha uses to deal with collisions in environments where no channel observation is possible. It uses a transmission throttling mechanism, the Backoff probability law beta sub I, a probability that is decreased as the number I of collisions increases. With the exponential Backoff, beta sub I is geometrically decreased. The binary exponential Backoff is used in the standards IEEE 802.3 and 802.11, where the exponential base is b equal to 2. Past work on this topic has appeared a few years ago. Here you can find the main references. From these works, it turned out that the exponential law is too aggressive in refraining from transmission. As a consequence, no delay moment exists for n greater than 2. Therefore, we need to investigate other, more favorable laws. The general analysis of the Backoff mechanism is quite difficult because too many variables are involved. We have to take into account variable x sub I, the Backoff indexes at each station, and then we have to take into account the Q length at each station. All those variables are strictly correlated and must be considered jointly. Furthermore, we have the number of stations that can go to infinity. This is a too complex model, which is why we don't have definite results. To simplify the analysis, we can use the saturation model, in which we assume that Q's are always full, so that only the Backoff indexes are used in the analysis. In spite of the simplification introduced, this model is able to provide exact results on the throughput delay performance when referring to a congested system, so it's very useful. In the saturation model, we use stages, such that stage I contains the users whose Backoff index is I. Users at each transmission are routed among the stages, as shown in this figure, where you can see collision probabilities alpha sub I and flow rates lambda sub I. The state of such a system is the vector of components n sub 0, n sub 1, and so on. This model is still difficult to analyze because we must derive the joint distribution of the number of users in the different stages. Thus, it happens that results are available only for specific cases, such as the binary exponential Backoff. A further simplification, largely used in the literature, assumes that the number of users at each stage is jointly distributed according to the Poisson distribution. This assumption greatly simplifies the analysis because now the numbers n sub I become independent. Their distribution is known and the collision probability becomes independent of index I. The key advantages in using this model are that all results are easily attained and we can investigate all the conceivable Backoff laws. On the other side, we get approximated results, which in the exponential case are underestimated. The general results we get with the Poisson model are resumed in this slide and hold for all Backoff laws. It turns out that the throughput is provided by this formula here, which is well known since it comes from elementary models. This equation provides the throughput lambda 0 as function of the channel traffic capital lambda and says that the maximum throughput is e to the minus 1, again a well-known figure. The channel traffic lambda is related to the number of users n by this equation, which, given the number of users n, has only one solution in lambda. Furthermore, the limit here tells the condition under which the Backoff law provides positive throughput, even when the number of users goes to infinity. In this work, we compare two Backoff laws, the exponential one and the polynomial one, and we compare them as their parameters change. However, in order to get fair comparisons, we have assigned the parameters b, I sub 0, and a in such a way that the throughput, when only one user is present, is always the same. We have chosen to set this bandwidth equal to 25%. In fact, we have proven in other works that with a greater value, in some instances, instability sets in. In this slide, we see the throughput results when using the exponential law. Our theoretical findings say that we always have positive asymptotic throughput, which is a big advantage. The figure shows different throughput curves with different values of parameters b and I sub 0. We see that the green curve with the parameters of the standard is never the best solution. Rather, the yellow and purple curves seems a better choice. And this happens when b lies between 1.2 and 1.6. In this slide, we see the throughput results for the polynomial law for different polynomial degree nu. Here, the asymptotic throughput is 0, and we must choose the parameter nu to fit the range of the number of users to be served. For example, if the users don't exceed 100, then nu equal to 2 is the best choice. Dealing with delays, since here we have full queues and the queuing delay has no meaning, we evaluate the access delay, which is the time between two consecutive transmissions of a user. In the exponential case shown here, we derive the complementary cumulative distribution function, which is shown in the figure, whose tail decreases with a power zeta that goes to 1 when n goes to infinity. In the binary case, the slope of the curves goes from 2 to 1, showing that no finite delay moment can exist for any n, and that again, the parameters in the standard are largely not optimal. Again, in the exponential case, however, the delay variance exists for values of the parameter b lower than 2 and for a limited number of users. This is shown in this figure, where we have reported the ratio between the standard deviation and the average value. We see that, in order for the variance to exist, we can admit no more than 3 users when b is equal to 1.6, and we can admit up to 18 users when b is equal to 1.05. In the polynomial case, things go much better. Here, the delay variance always exists. It increases with n and increases more sharply with the power nu. Still, in the polynomial case, to get more insights, we plot the delay standard deviation versus the channel traffic in the 4 cases corresponding to nu equal to 1, 2, 3, and 4. We have also plotted with the dashed green line the throughput curve, which is independent of the parameter nu, and whose axis is shown here on the right. If we want a throughput no less than 30%, in correspondence of the channel traffic that provides 30% throughput, we read 4 values for the standard deviation corresponding to the 4 values of the parameter nu. However, changing nu with the same traffic lambda also changes the number of users n, and therefore we can plot these 4 values for the standard deviation versus 4 different values of n when nu changes from 1 to 4. Here we see the plot of the 4 points derived in the previous figure. Their values have been interpolated for fractional values of nu. We see that as the number of users increases, to fulfill the 30% throughput requirement, we must increase nu, and thus increase the standard deviation of the access delay. For example, with 1,000 users, the standard deviation is about 8 times the average, a rather high value. To validate our theoretical analysis, we obtained some simulation results to compare with our theoretical ones. As an example, this figure shows the throughput and the standard deviation for the polynomial case with a equal 4 and nu equal 2. Simulation results are reported as small circles and squares, and, as we can see, somehow fit the analytical curves, although not exactly. This was expected because of the simplification we have introduced in our model. So far, we have reported the results about the stationary behavior of the protocols, but we have also investigated some transient situations. We ran some simulations measuring the average time it takes to end user to send one packet and only one packet each, using 2 laws, the binary exponential Backoff and the polynomial Backoff with degree 2, starting with all 0 Backoff indexes. This figure interpolates the results and shows that for all values of n, the polynomial case is better than the exponential one, and for large n, the polynomial one is largely better. Here we draw our conclusions. The exponential Backoff is overreacting, showing that the base should be kept to a minimum. It can deal with any n up to infinity, but its delays are not practical. On the other side, the polynomial Backoff requires a limit on the maximum number of users, but presents much more favorable delays. We saw that second-order polynomial is a good candidate for 100 users. This concludes my presentation. Thank you for your attention.